Hello students, welcome to the EN 401 lecture on metals and material failure. Here's the roadmap for this lecture. We're going to talk about metals and alloys. Then we're going to go specifically into steel, aluminum, and then some other metals. We'll talk about galvanic corrosion and then material failure modes with an emphasis on brittle failure. So what is a metal? So a metal is a material where all of the molecules or atoms of the metal share a metallic bond, and some typical properties of metals are they're hard, shiny, malleable, fusible, and ductile, and they typically have good electrical and thermal conductivity. So what's the difference between a metal and an alloy? Well, if we were talking about an elemental metal, that means we have just one element that makes up the entire metal. So some type of elemental metal might just be iron. But then, typically our elemental metals don't have great engineering properties. So what we do typically is mix other either metals or other elements into that elemental metal, and we make what's called an alloy. So alloys are great because it's sort of a recipe for a metal that has the ideal engineering properties for our application. So we've got a nice big recipe here on the bottom. If we take some manganese, iron ore, chromium, and carbon, and we mix those together in the right ratios and in the right process, we can end up with stainless steel. Right? If we had iron all by itself, it's not very stainless. Pure iron rusts pretty easily. So we've got two basic types of metal alloys. We have substitutional alloys and we have interstitial alloys. So in a substitutional alloy, we have essentially two different types of metals where the atoms are a similar size. So here's our substitutional alloy here in this picture. So maybe this is a steel with iron and some copper in it. So the iron atom and the copper atom are about similar size. So the copper atom would replace an iron atom in the crystalline structure of the metal. In our interstitial alloy, like we have over here in this right picture, maybe this is iron and these are smaller carbon atoms, and those fit in between in the crystal structure. The carbon fits in between the iron atoms in the crystal structure. Now you might be asking, can you have an interstitial and substitutional alloy? And the answer is yes. Yeah, you could have both carbon and copper in an alloy where the main alloying element is iron. So you could have both. So steel is one of the most widely used engineering alloys and materials in the world. There's a great video right here, so go ahead and pause here and watch this great YouTube video on what steel is and how it's made. Welcome back. So steel, again, great material. Lots of different recipes for steel to make all different types of alloys for pretty much any type of application. And a great thing about steel is not only can we change the recipe for our steel to get different properties, we can also adjust steel properties by doing heat treatments and cold working. So we got a video on that, but yeah, also you can change the recipe, which is these two bolts right here. So every metal essentially is made up of tiny grains of the main alloying element and everything else that's sort of been tossed in there. So we got some pictures down here of different grains of or grain structures of steel. So that's pretty much what all metals will look like. They'll all have some type of grain. So go ahead and watch this video here at the top. It'll tell you more about metal grains and how we see those and how metals are treated and worked. So go ahead and pause here and watch that video. All All right, welcome back. So yeah, hopefully in the video you saw that we can cold work metals, right? So that stretches the metals out, usually in some kind of rolling press, and that stretching causes some plastic deformation and strain hardening. Some really good examples of cold work metal are body panels on your car. They're made by essentially large presses or large rollers. You take a big flat piece of sheet metal and you press it with some type of pressed or molded press, and that bends the metal permanently deforms it, straight hardens it, so it gives your body panels in your car some rigidity. I saw we can also heat treat steel so you can quench it, right? In the video you should have seen that you have to have enough perlite in your steel to quench it. You can always temper steel, so we saw that tempering steel allows new grains to grow, new smaller and more uniform grains. Quenched and tempered steel usually gives you a nice strong product. And then you also saw that steel has two main types of grains: perlite, and so that's that carbon plus iron, and that's going to give you properties of hardness and strength. But too much perlite, you could end up with a brittle steel. And then there's also ferrite, which is mostly just iron, and that gives the steel properties of ductility. But ferrite isn't quite as strong as the perlite. So steel is designated by two different main societies. There is ASTM, American Society of Testing and Materials. So ASTM gives names to steel. All the names start with an A, right? So A, that means that the metal is ferrous, and if it's ferrous, it's most likely steel. So all of our steels are going to, if they have an ASTM spec, are going to be A. And then there is some number that follows it. It's an arbitrary and sequential number. One steel we like to use for the class is A36 steel. It's mild carbon structural steel. It's used all the time. You'll see a case study at the end of the class where a bridge is made from A36 steel. And the nice thing about A36 steel is its yield strength, or maximum stress that it can take before plastic deformation, is 36,300 psi. So A36, 36,000 psi, pretty easy to remember. One thing, steels are iron based alloys with less than 2.11% carbon. So cast irons have more than 2.11% carbon. So that cast iron pan you have at home, the reason it's so dark in color, has lots of carbon in it, right? Carbon has a dark color, so you mix that into your steel with enough of it, everything's going to be kind of dark. ASTM also has names for other metals, so it also has aluminum, titanium, copper-based alloy metal names. So ASTM's got all those in there. There's also the American Society of Automotive Engineers, and they have their own designation system. So in SAE setup, the first two numbers tell you what the main alloying element is, so you don't have to know these off the top of your head. Just know that those first two tell you what the main element is, and then the last two tell you the amount of carbon in it. So a 1020 steel means manganese is the primary alloying element, and it's 2.2% carbon. So 1045 steel would have 0.45% carbon, 1018 steel 0.18% carbon. And we saw from that video that changing the carbon content changes the strength and also changes the brittleness. So a lot of different material properties can change in steel just by changing the carbon content. All right, so here's a non-comprehensive list of some different types of ASTM steels, and you can see that they all have different types of applications. So go ahead and take a look at these. So here's a typical material test for a steel. So you should have seen already that metals are typically tested doing a tensile test, right? So we do our tensile test, we put it in our tensile testing machine, we apply a force to it, and then as we apply a force, we get stress and strain, and then we get to a point where that stress and strain relationship is no longer linear. We call that the yield point. So remember, beyond the yield point, we're going to start to see plastic deformation. And then we get this flat little slope here, right? And so in this region of our tensile test, what's happening is the steel grains are sort of realigning and reconfiguring because of the amount of stress that they have felt. And then eventually they get realigned and reconfigured, and the steel begins to take more strain, more stress. So we call this region the strain hardening region. So you can see right here there is more stress being taken than at our yield point. So the material actually got stronger through this test, which is very typical for steel. This point here is the ultimate tensile strength of the material. Once we get into this point, our specimen, the cross-sectional area that typically starts to thin out, right? We call that thinning out of the cross-sectional area necking. You should have already seen a video on that, and then eventually it fails. So this is just, I said, it's a pretty typical material test for a steel specimen. There are also some other tests we'll talk about later in this presentation. So aluminum, another great metal that's used in a lot of coastal projects. Aluminum has, some similar properties to steel, so it's very strong. But the thing that's great about aluminum is it's typically corrosion resistant, much more so than ferrous alloys other than steels, and it is much lighter weight than steel is. So we see aluminum in all types of coastal projects. One of the downsides of aluminum is it's not quite as strong as steel, and it also fatigues differently and is more susceptible to brittle types of failure, which can be catastrophic. So aluminums are identified just like steel, as they have some type of numbering system. So here's some generic numbers. There's also tempered designations for our aluminum. So here's a couple tempered designations. So F is as fabricated, so just a cast aluminum, or you could have strain hardened aluminum, which would have an H. Or let's say you have this T, or this 6061 T6 aluminum, that would be a heat treated aluminum. So this link here has all the designations for aluminum and what all the numbers mean. So here's a typical tensile test stress strain chart for aluminum. And what we can see is aluminum reacts a little bit differently than steel does. We don't have that up and then down and flat line like we had in our steel sample. It's just kind of linear here and gently slopes and then breaks. So typically aluminums don't take quite as much strain as steels do before fracture. So aluminums, we could say, generally are less tough than steel. That's why we don't see a lot of aluminum-hulled submarines or aluminum-hulled aircraft carriers. It's just not quite as tough. One thing that's great to see on this graph here is this correlation of Young's modulus when we pass the yield point. So here's our aluminum yield point. Right, so let's say we stressed a material to some stress beyond aluminum's yield point. So right here, and let's say we take the stress off right here. So instead of following this curve back down to 0, the material would follow a parallel line to the Young's modulus, and we'd have some new permanent strain in our material here. So that's good to know that if you stress something past the yield point, when you take that stress off, the material will shrink back down and follow the Young's modulus back to a new permanent strain. So obviously, steel and aluminum aren't the only two types of metals. So here's a nice list of some other metals that are typically seen in coastal projects. One that you may have heard of that's used a lot is zinc for cathodic protection. So zinc, a lot of times, there's big plates of zinc that are stuck on the sides of ships or sides of bulkheads, seawalls to help keep the steel from corroding. So here's a list of a whole bunch of different types of metals and some of their properties. So tensile testing isn't the only test that we run on metals. We have two other types of tests that are often run. One is called the Charpy V-notch test. So the Charpy V-notch test is a high strain rate test where you take a hammer. So here's kind of a diagram of the Charpy V-notch test, and you take this hammer, you pull it to the starting position. At the starting position, we know how much potential energy it has. We put a small test specimen that looks at like this into the machine, and then we drop the hammer. If the specimen didn't absorb any energy, then the hammer would swing through and come back to the same exact height that it started at. But the more energy that the sample absorbs, the lower the hammer goes on this follow-through swing. So if, say, our specimen was really tough and absorbed all the energy, the hammer would hit it and stop here. And if it's really weak, the hammer would swing through and go here. So go ahead and watch this video here for the Charpy V-notch test, and that'll kind of show you some different metals and how they react in this toughness test. There's also another test that's run is for hardness. So here's three different variants of a hardness test. So hardness kind of tells you how good is this material at resisting localized plastic deformation. So maybe how good is it, another way to think about it is how good is it at resisting scratches. So toughness and hardness are not the same things. They sort of sound similar, but they're not. So toughness is the ability to absorb lots and lots of energy before fracturing, and hardness is ability to resist localized plastic deformation. So maybe a sort of clear example is maybe a ceramic tile or a porcelain tile. So just think about some kind of floor tile. So typically really hard materials, right? But if you've ever held one and dropped it from 2 or 3 feet off the ground, as soon as it hits the ground, it's going to shatter on you. So really good for you to walk on and not get scratched. But as soon as you drop it, it will break, right? So it's a hard material but not tough. And then on the other end of the spectrum, really tough material is copper. So if you've ever worked with or seen copper piping, copper's bent in all different types of directions, and it's really easy to bend. But copper also is really easy to scratch. So if you take a good close look at that copper, it's probably covered in scratches. So copper is not very hard, but it's very tough, right? So you can bend it to do lots of water piping, but be careful with getting anything that's sharp around. You could cause some scratches to it. All right, so multiple metals. If you get multiple metals put close together, you can get what's called a galvanic reaction. And what essentially happens is the atoms from one metal will be pulled off, and it'll cause corrosion from one metal, and they'll sort of attach to the other metal. It's actually a pretty prevalent problem. The Navy's experienced this problem with the LCS. You've got an aluminum hulled vessel, and it has steel cross bracing, and where the steel connects to the aluminum on the ship, if that gets a little bit wet, it causes this galvanic corrosion. And they've actually had issues where holes have opened up in the side of the LCSs because of this galvanic corrosion. So one way to that the Navy has at least dealt with this is they've used zinc sacrificial anodes. But here are a couple of different methods to reduce galvanic corrosion. So the first one is just pick materials that are better off to be placed next to each other. So we'll take a look at that table on the next slide. So this table, kind of in a simple manner, classifies these metals in order of electric potential when placed into flowing seawater, which is an electrolyte solution, so it allows electricity to flow. So the closer these metals are in this simple table here, the more electrically similar they are. So magnesium and zinc are probably pretty safe to put in seawater together and not see a lot of galvanic corrosion. Whereas if you put, let's say, calcium and platinum in water together and salt water together, you'd see a lot of galvanic corrosion. So the closer they are, the less likely to see extensive galvanic corrosion, and the further apart they are in this list, the more likely. All right, so material failure. So here's pretty much all the flavors of material failure. So let's kind of go through these. So fatigue is repeated cyclic loading that leads to failure. So go ahead and watch this video. This is pretty cool to watch a fatigue failure. Corrosion failure. Corrosion a lot of times just opens up the floodgates for other types of failure. So essentially you'll corrode the material, you reduce the cross-sectional area or open up holes, and that'll cause the material to become weaker. You're going to get fracture, both ductile and brittle. Buckling, which is a sudden sideways instability. So if you ever stepped on a soda can and it didn't crush straight down, you probably saw some buckling. We can get shear failures. So you get some kind of failure along a specific plane. Remember that plane would be potentially parallel with the forces being applied. And then creep. Creep is a slow deformation failure due to continuous static loads. That's what we kind of have going on in the bridge here. It just has this continuous load of its own weight and the cars that kind of overpass it, and you can see the bridge has started to sag down just a little bit here in the middle, and over time it'll continue to sag and sag until the bridge is either no longer usable or it fractures. So here's some pictures of these different fracture types. So ductile versus brittle failure. So brittle materials, when they fail, it's usually pretty unexpected. It's hard to guess how or where they're going to fail. So pretty unpredictable, and oftentimes they fail catastrophically. So brittle failures are not great things to deal with. Ductile materials, you can typically see that they're starting to fail. You'll see cracks or huge deformations before they fail. So when we design buildings, we like to design them to fail in a ductile manner. You want to see that the building's going to fail. You don't want to be in there and then all of a sudden it just falls on someone's head. So we try to do ductile failure analysis for buildings and not brittle failure analysis. So metals and other materials can also undergo what's called the ductile to brittle transition. So essentially, as temperature goes down, some materials that used to be tough and be ductile, as the temperature decreases, they become not tough and very brittle. So go ahead and watch this video here and click on this link here to see how the crystal structure of a metal determines if it's going to have a ductile to brittle transition or not. So big case where ductile to brittle transition costs a lot of lives was the Titanic. So the hull was made out of a carbon steel that underwent ductile to brittle transition at a relatively high temperature. As it was transiting the North Atlantic, the metal became brittle, and then when it hit the iceberg, instead of just bending around the iceberg, it shattered and it allowed water to come in and caused the Titanic to sink. And here's some other brittle fracture examples. So brittle fracture, if you read through these examples, you'll see is very catastrophic and unforeseen, and that's the big problem with brittle fracture. So here's an example, and here's another example of a brittle fracture that led to this bridge falling. All right, so here's the review. Hope you enjoyed the lesson, and thanks for watching.